In this video, we'll look at the graphs of the parent functions for the rest of our trigonometric functions, namely tangent, secant, and cosecant. We'll begin with tangent. Much of the way we construct this will be like we've done already for sine and cosine. As you'll notice, we'll graph two periods for this particular graph here. And so, like we did before, we can start by marking off the axes. Of course, we have our x-axis here horizontally, our y-axis vertically. And if I want two periods, of course, we have to recall that the period of tangent is, that's right, pi. That's one period. So two periods would take us all the way out to 2 pi. And then we're going to use the same practice we did with sine and cosine, which is start to cut the axis marks in half. So, of course, we have 0 at the origin. Halfway between 0 and 2 pi would be 1 pi. And then we'll cut all those marks in half again. So between 0 and pi, we'll have pi over 2. And then between pi and 2 pi, we'll have 3 pi over 2, or 1.5 pi. And so we'll mark the axes as shown, but this time for tangent especially, I'm going to go even one marking to the left of the origin. As you'll see, it just turns out to work out nicely for the picture. So this was pi over 2, going one mark to the right. That'll mean that this is negative pi over 2, going one marking to the left. All right, now to start putting some things on this graph, let's recall what tangent of x even means. Of course, we know this is defined as sine of x divided by cosine of x. And since we know sine and cosine so well now, we're going to use those to graph tangent. Now, one of the first things we typically do when graphing sine or cosine is mark the intercepts on the x-axis to get at least something going for our framework. This time, we're going to change that up a little bit, though we are going to mark the intercepts. I'm actually going to start with something else. Notice in this fraction defining tangent as sine over cosine, we have a denominator as cosine of x. Now, what happens when a denominator is equal to 0? Bad things, that's right. We actually don't have a defined value when the denominator is 0. Well, what that's going to create for us are some vertical asymptotes. So we can figure out exactly where to put those based on when our denominator, in this case cosine of x, is 0. All right, so you might need to pull out the unit circle to recall some of these things. Just a quick sketch might help. Cosine is the x-coordinate of all of our points around the unit circle. That would be 0 either up here at pi over 2 or down here at 3 pi over 2. So let's go ahead and mark those. We know already right here is pi over 2. I'm going to put a vertical asymptote there. And we'll have another one over here, as I mentioned, at 3 pi over 2. All right, now you can start to see some pattern. For instance, the distance between these vertical asymptotes is 1 pi. From pi over 2 to 3 pi over 2 is a distance of 1 pi. So if I continue that same distance going to the left of pi over 2, that means I would have another vertical asymptote here at negative pi over 2. So I'm going to put that one in. So far, we have the vertical asymptotes plotted based on when our cosine values are 0, because we can't divide by 0. Those would be undefined, creating these vertical asymptotes. Now let's talk about the intercepts. That would be when our tangent values are 0, which is when sine of x is 0. Of course, again, on the unit circle, you can just do a quick sketch. Notice that happens at 0, pi, and of course back to 2 pi, which is the same as 0. So I should be able to put an x-intercept at 0, an x-intercept at pi. And of course, you can tell the pattern here is that every multiple of pi will have an intercept. So I would even have another one here at 2 pi, but that'll be more than we need to graph. You can graph it there if you'd like. But this will give us a full 2 periods. All right, now, what I want to do to get some more points on this graph is take the markings we currently have on the x-axis and cut each of those in half once more. You might recall we've done this for sine and cosine. We're doing it here again. From 0 to pi over 2, cut in half, will leave us at pi over 4. And then if you just count by fourths to get the pattern, this is 1/4 pi, 2/4 is 1/2, 3/4, so 3 pi over 4 is between pi over 2 and pi. 4 pi over 4 would be at pi. 5 pi over 4 is next. 6 pi over 4 is 3/2. We got it. And so on. Now, negative in the negative direction between 0 and negative pi over 2, of course, would be negative pi over 4. All right, so marking all of those marks, which are halfway between all the halfway marks we did originally, will help us fill out the picture quite well. As you might recall, with tangent, if you remember those values going around the unit circle, at these quarter marks, negative pi over 4, pi over 4, 3 pi over 4, those are when the tangent values are either positive 1 or negative 1. Now let's recall a helpful hint from the unit circle about tangent, which is in which quadrants are tangents positive or negative? You might recall that in quadrant 1, tangent values are positive. In quadrant 2, they are negative. Quadrant 3 is positive again. And quadrant 4 is negative also. So quadrants 1 and 3 positive, 2 and 4 negative. Now that's going to help us as we try to mark some more points on this. For instance, at pi over 4, the tangent value is positive 1. That's right. So I'm going to put a mark for positive 1 on the y-axis and then put a point up there when x is pi over 4. That's quadrant 1. You can tell over here by the unit circle sketch. The next marking I have here going to the right, the next quarter marking I see is 3 pi over 4. That's quadrant 2, which means my output value will be negative 1. So again, the nice thing about all these quarter marks for tangent is that the values there are either 1 or negative 1. If I keep going to the next mark, 5 pi over 4, this is now quadrant 3, which will give me an output, again, of positive 1. Moving on would give us more this way, which I don't have marked. So let's go back to the negative side here. To the left of 0, at negative pi over 4, if you can imagine where that is in the unit circle, that'd be over here in quadrant 4. So that'll be a negative value, negative 1. All right, so the points we have here are enough to plot two periods of tangent. The way we're going to connect these dots we see now in each span of vertical asymptotes is with curves that approach the asymptotes as they go up and down. So they turn out to be these snake-like curves that approach the asymptotes in each direction. To the right, it's going to approach this vertical asymptote going up. To the left, it would approach this one going down. It ends up with a curve somewhat like this. Again, my hand drawing is not perfect. The next one will look the same. It's a curve that cuts through the intercept in this way. So this is the graph for two periods of tangent of x. Now I'd like to make note over here in this empty space in the bottom right corner of a couple things. First of all, let's see if we can describe the domain of this function, the parent function tangent of x. Now, as you might recall, domain pertains to the x values, or the inputs that we're allowed to use for the function. And if you take a look at this graph, there are a lot of things we are allowed to use where the graph exists, but there are a few things we're not, and those would be exactly where all the vertical asymptotes are. So our domain, we could write in set notation, and in set notation, we'll use the curly braces. Our domain is defined as all x's such that, and the vertical bar means such that. Now we're going to describe which x values we want, and we basically want everything except where the vertical asymptotes occur. So you can kind of see the pattern here. So we'll define that by saying x is not equal to, or cannot be. If you start at pi over 2, you'll notice that they just count the spans between the vertical asymptotes, just count up by pi, or multiples of pi. Pi over 2 plus pi is 3 over 2, or pi over 2 minus pi is negative pi over 2. So we can say x can't be pi over 2 plus, we'll call it k pi, as we've seen that before. That means any integer multiple of pi. And so we can define our domain in set notation in that way. That basically means any x value except pi over 2 plus any multiple of pi, to the right or to the left. Now, the range of this graph could also be defined, but it's even easier. You might be able to tell that vertically, within one of these little spans between asymptotes, the graph goes down forever, as indicated by these arrows, and up forever also, meaning it doesn't actually skip anything. So our range would be up and down forever, also known as all reals. There are some other ways to write all reals, but I'll just write those words. That's good enough for now. All reals. Now let's take a look at the graph of cotangent, the parent function cotangent of x. And once again, we'll do 2 periods of this function also. Remember, 1 period for cotangent is also pi, just like tangent. So 2 periods will take us out 2 pi. I'll mark that on our axis just to get a nice framework of where we're going. Of course, we have our x and y axes here. And then, like we've been doing, we'll start cutting things in half to get some more markings on here. So halfway between 0 and 2 pi would be 1 pi. And halfway between those will give us pi over 2 and 3 pi over 2. Now, once again, let's recall what the definition of cotangent is so we can start to know where our asymptotes should go and where our intercepts should go. Cotangent, as you know, is defined by cosine of x over sine of x. It's the reciprocal of tangent. Let's determine where our vertical asymptotes would be first. Those will occur when our function is undefined, which of course occurs when sine of x is 0, because we can't divide by 0. A quick unit circle sketch, again, is never a bad idea, just to make sure we're on the right page here. So sine of x is 0, that's all the y coordinates, when we're at 0 or pi or 2 pi or any of those x-axis places. So again, this will be our vertical asymptote locations where sine of x is 0, and we just decided that that would be when x is 0. So right at the y-axis, there's a vertical asymptote. It also occurs when x is pi. And it would occur when x is 2 pi. And I'm going to do one marking to the left of the origin also here, like tangent, just to make sure we understand that these graphs do go on forever left and right, but we're only graphing really 2 periods of this. So this should be plenty, and we know those are the vertical asymptotes. Halfway between each vertical asymptote, just like tangent, is where all of the intercepts should occur. So we can just go ahead and mark those. We know that they're halfway between where the asymptotes are. And then if we mark halfway between all those current markings, we'll be able to tell where the 1 or -1 places are for this function. So of course halfway between 0 and pi over 2 is pi over 4. So that's now counting by fourths. 1/4, 2/4, 3/4, 4/4 is pi. 5/4 or 5 pi over 4, 6/4 is 3/2, 7/4 or 7 pi over 4, and if I want I can do a negative pi over 4 also, just to span this out here. That should be plenty. Now all we have to do is recognize which values or which quadrants are positive and negative for cotangent. Now of course cotangent is just 1 over tangent, which means the signs of the values for cotangent are no different for those of tangent in the various quadrants. So quadrant 1 is positive, quadrant 2 is negative, quadrant 3 is positive, quadrant 4 is also negative. All right, so any value that's in quadrants 1 or 3 will give us an output of positive 1. Any value in quadrant 2 or 4 will give us an output of negative 1. All right, so you'll recall pi over 3 is quadrant 1, so that's a positive 1. 3 pi over 4 is quadrant 2, so that's a negative 1. And this pattern continues. Up at 5 pi over 4, we get positive 1, 7 pi over 4, negative 1. And you'll notice the repetition here between one period to the next. The points start high, go to the intercept in the middle, and then low. This is, as you'll also notice, the opposite of what happened with tangent. Tangent started low, intercept, and then high from left to right. Cotangent from left to right goes high, intercept, low. So just recognizing those little patterns is helpful. If I connect these points in shapes that are similar to tangent, you'll notice they hit the intercepts and then approach the asymptotes in either direction, giving us graphs that look somewhat like this. So starting high to the left, ending low to the right, between each span of vertical asymptotes, and those spans, of course, represent 1 full period, which is pi. We now have 2 full periods graphed on this picture, which is from 0 to 2 pi. Let's also try to sneak in the domain of this function and the range here in the bottom right corner with a little bit of space. This time the domain will also define in set notation like tangent. It's all x's where x is not equal to any multiple of pi, so we'll just call that k pi. So x cannot be k pi, and the range, just like tangent, will be all reals. Let's now take a look at the parent function graph for secant of x, y equals secant of x. Now, just like tangent and cotangent, we're going to recall what secant even means, which is 1 over the cosine of x. That's going to help us put this graph down. Now, let's recall that the period for secant is 2 pi. And so if I want to go 2 periods, then I should go all the way out to 4 pi to make sure we have enough space here. And now I'll mark all the halfway places. So between 0 and 4 pi, of course, is 2 pi. And halfway between what's left there would be pi and 3 pi. So we're just counting up by pi's from 0 to 4 pi on our x-axis currently. And then let's, of course, cut all those places in half one more time, giving us pi over 2. Now if I count by halves, I have pi over 2, 2 pi over 2, 3 pi over 2. 4 pi over 2 is 2 pi, and then 5 pi over 2, 6 pi over 2 is 3 pi, and then 7 pi over 2. And this should give us plenty to work with on our axis for now. All right, now let's go back to the definition of secant and recall that secant, just like tangent and cotangent, also has places where it will be undefined because you're dividing by cosine, and so when cosine is 0, we have a problem. Well, if you pull out your unit circle and just refresh where cosine is 0, that occurs over at pi over 2 or 3 pi over 2, the top and bottom of the circle. So at those places, let's mark them down now, namely pi over 2, we have a vertical asymptote because we're dividing by 0 at that point, 1 over 0. Also 3 pi over 2. And once you get the pattern of where these vertical asymptotes go, you can just keep continuing that. So you'll see they occur every multiple of pi, right? From half pi or pi over 2 to 3 pi over 2, that's adding pi. Or as we've drawn it, that's every other tick mark on our graph. So I should expect another vertical asymptote at 5 pi over 2, and yet another one at 7 pi over 2. All right, so that takes care of a vertical asymptotes. We could also, if we wanted to, extend one marking to the left and go at negative pi over 2, but this should be plenty to graph a full 2 periods. So now let's take a look at where the intercepts might occur. 1 over something will never be 0. So actually, there are no x-intercepts for secant. Instead of graphing intercepts, here's how we're going to construct the graph of secant. Since secant is 1 over cosine, I actually would like to graph cosine. Yes, just the basic parent cosine graph, which we already know. We know that goes from -1 at the bottom to +1 at the top. And let's recall what that graph looks like. I'm going to graph it with a dashed curve because it's going to help us construct secant, but I really wanted to look at it on this graph. So as you might recall, cosine, if I were to graph, starts at +1, and a full period of cosine is 2 pi. So then back at 2 pi, it will also hit +1. In the middle of that first period from 0 to 2 pi, at pi, it hits its minimum of -1. And then at the half pi mark, so pi over 2 and 3 pi over 2, we hit the intercepts. Okay, so I'm going to graph, again, just in a dashed curve here, what the graph of cosine would look like. We've already been graphing cosine and sine, so hopefully we're familiar with those curves. I'm also going to continue that pattern. As you can imagine, this would continue to go with another intercept at 5 pi over 2, another minimum at 3 pi, another intercept at pi over 2, and then a maximum at 4 pi. And let me continue one more period, again with a dashed curve, to connect these cosine points. All right, so I know we're not actually trying to graph cosine. We're trying to graph secant. But recall up here that secant is defined as 1 over cosine. So the easiest way to graph secant is to graph cosine like we just did, but with a dashed curve. Then, at any of the max or mins, we're going to create little U-shaped curves that stay within the asymptotes and run away from the graph of cosine. So at a maximum, for instance, it'll hit there and bounce back up, heading toward the asymptotes on each side. At the minimum, same thing. And then at this, I'll do this next minimum here at 3 pi. Again, we're going to have a downward U-shaped graph that's going to chase the asymptotes on each side, but use the minimum points there. So then, to get a full 2 periods, I'm going to do half of the first piece we have. At 0, there's a maximum value of 1 for cosine, which means that's where secant would hit and then run up toward the asymptote. Of course, the rest of this graph would go in the negative zone here, which you could do, but this is enough for 2 full periods. And even this last chunk here at pi over 4, there's a max, so we would expect a U-shaped graph to hit there and go up in that direction. Again, running away from the cosine graph, all the arrows are chasing away from it toward the asymptotes using the maxes and mins as their points. Those are the only points you actually need to graph for a graph like secant, just the mins or the maxes to know where the U-shapes should be. That and the asymptotes should be plenty. Now let's also talk about the domain and range of this secant graph. Now the domain, of course, will be anywhere we don't have vertical asymptotes. So that's basically where x is not equal to. As you can tell, they start at like pi over 2 and then increase by pi each time. You could also go to the negative direction, which is not plotted here, but it goes on forever each way. So we'll say x is not equal to pi over 2 plus k pi, where, again, k is any integer, positive or negative. That basically defines where all the asymptotes occur. So our domain would be anything but those. And then lastly, our range. In this case, now take a look carefully. Range is all the y values used. There's nothing being used between the positive 1, which is the minimum of all these upper branches, and negative 1, which is the maximum of all these lower branches. So all this space in between is not being used vertically. One way to write that is that all of our y values in absolute value form, so the absolute value of y, has to be greater than or equal to 1. Let's now take a look at the graph for the function, the parent function y equals cosecant of x, and we'll do 2 periods here as well. You'll start to notice a lot of similarities between this and secant. So, of course, let's start by defining exactly what cosecant mean. You might recall cosecant is 1 over the sine of x. That will help us determine exactly how to plot the asymptotes here because, of course, we can't let sine be 0 for this so that it's undefined. So our x-axis and our y-axis will be labeled for 2 full periods. The period of cosecant, as you might recall, is 2 pi. So if I take that out 2 periods, let me go all the way out to 4 pi and start cutting things in half. So we have 0 at the origin, 2 pi between that and 4 pi, and then between 0 and 2 pi, of course, halfway is pi, and then between 2 pi and 4 pi would be 3 pi. And then we'll cut all of those places in half once more. Hopefully you're starting to get the hang of this axis plotting stuff. It's very important for these. Now I'll be counting by half pi's, so pi over 2. 2 pi over 2 is pi. 3 pi over 2 is next. 4 pi over 2 is 2 pi. 5 pi over 2 is next. 6 pi over 2 is 3 pi. 7 pi over 2 is next. And then, of course, 8 pi over 2 is 4 pi. All right, this should give us plenty to work with. Now, the asymptotes will occur where our function is undefined, which is where sine of x is 0, since that's what we're dividing by now. So let's just do a quick sketch of our unit circle. Where is sine 0? Well, that's on the x-axis locations, which of course is 0, pi, and any multiple thereof. So we'll have vertical asymptotes for this cosecant function at pi, at 0, which is right on the y-axis. And then adding pi from there will take us to 2 pi, 3 pi, and 4 pi. All those places are where sine of x is 0. Now, as you might recall with the graph of secant, secant is 1 over cosine. We actually used the graph of cosine to graph secant. In the same way, since cosecant is 1 over sine, we're going to use the graph of sine to help us graph cosecant. So let's just do a parent function sine graph. You might recall the parent function for sine has intercepts at 0, pi, 2 pi, really any multiple of pi. I'll just keep those going all the way through. And then it will hit its maxes at 1 and its mins at -1 at all the half marks in between that. So it starts at the origin going up, hitting a max when x is pi over 2, back to the intercept at pi, min at 3 pi over 2, intercept at 2 pi, and so on. The pattern just continues. So I'll follow it to get our points plotted. And then remember, with a dashed curve, I'd like now to draw the sine parent function, because this will help us construct our cosecant function, which is 1 over that sine function. All right, so just like with secant, at all the max and mins, we're actually going to use those points to generate these branches, which look just like they did for secant. They're going to be U-shaped branches that stay within the asymptotes and actually chase the asymptotes in the direction they're going each time. So the first branch between 0 and pi is a U-shaped graph going up to the left to 0, up to the right toward pi, and then the second branch between pi and 2 pi is the opposite. It'll be a downward U-shape chasing the asymptotes to the left and the right vertically, which is going down for these. And then the pattern just continues. So in each of the next spans between asymptotes, I'm going to put some U-shaped graphs that chase the asymptotes accordingly. All right, so what is graphed now in the solid curves is the graph of cosecant. Of course, let's finish by discussing domain and range. And so the domain of cosecant would be anywhere that x occurs, which is basically everywhere except the asymptotes. As you'll notice, in this case, the asymptotes occur at all multiples of pi. So we'll just say x can't be k pi, any integer multiple of pi. And for the range, kind of like we did for secant, we'll use the same idea here. Any y value has to be greater than or equal to 1 or less than or equal to -1. So the way we define that is that the absolute value of y has to be greater than or equal to 1. That covers both sides, above and below.